Mechanical engineering labs at Georgia Tech present unique challenges of scale. We have two core lab courses with 280 plus students per semester per lab course. Unfortunately, the courses have historically been two of the worst rated across the Georgia Tech campus. We redesigned our experimental methods class into a scaffolded set of 2-week experiences. Most of the background content is covered prior to week 1 through lectures, videos, and other resources. A homework assignment also provides a scaffolded introduction into lab content. The homework provides guided questions which help students relate physical system interactions to sensor output and program myRIO controllers to interface with the equipment's sensors. When students arrive in lab for week 1, they interface their myRIO controller with the lab's physical sensors and actuators. This includes identifying needed circuits and signal conditioning elements, calibrating sensors, and determining theoretical meaning from experimental signals. Between week 1 and 2, students are given a challenge to solve or answer during week 2. This could be to determine the yield strength of a test specimen, to locate an object using sonar, or to determine a way to reduce vibration of a beam and a particular frequency of excitation. Students are also given another homework assignment which asks guiding questions to help them formulate a process to solve the challenge and to create a myRIO program to help collect and process data. During week 2, students run their experimental procedures, iterating as needed until they have the results they feel they can trust. Finally, after week 2, students create deliverables, worksheets, or executive summary reports, which explain their process, results, and confidence in the answers they provide. This report covers both weeks of labs, rather than requiring large written assignments each week. As far as the labs themselves, weeks 1 and 2 focus on signals, instrumentation calibration, and tying physical motion of a mass spring damper system to sensor data from force transducers and magnetic displacement sensors. This provides an introduction to thinking about input-output systems and changing inputs, i.e. excitation speed, to determine the effects on an output. Weeks 3 and 4 of lab focus on vibrations, and more specifically the vibration of a fixed free beam as measured with a laser Doppler vibrometer. This allows students to dive deeper into input-output relationships, transfer functions, and complex ideas like harmonics and mode shapes. All sensors and actuators connect via B and C cables to custom fabricated myRIO interface boards, which greatly simplifies wiring for students. In weeks 5 and 6, students focus on destructive testing to determine the stress-strain characteristics of various materials. This provides an opportunity to build a force transducer from a metal blank and a strain gauge, to determine the signal conditioning needs, for example, Wheatstone bridge and amplifier, and to calibrate their new instrument using known masses and geometric force amplification. The stress-strain test stand is capable of roughly 65 kilonewtons, or around 7 tons of force. That is just over the combined weight of 2 mid-sized cars, which enables students to test real-world products like bolts, chains, and climbing slings. The stand also provides a handle for straining the test piece, allowing the students tactile feedback on the amount of force applied to the test piece and greatly increasing the students' intuitive understanding of stress and strain. In weeks 7 and 8, students focus on making acoustic measurements. They begin by accounting for the floating nature of microphone signals and identifying useful portions of acoustic recordings. They then determine the directivity of sound and its relationship to frequency by measuring the acoustic volume or amplitude at various angular offsets from the center line of the speaker. Finally, students measure the experimental speed of sound and use sonar to determine the location of an object in 2D space. All measurements are taken on the myRIO, and the myRIO processes the incoming data to provide an intuitive interface for exploring the acoustic behavior without confusing students with complex burst signal creation, triggering, and overlaying. The beauty of the myRIO in all projects is that it allows us, the instructional designers, to create exactly the student experience we want while removing distracting information. For high-achieving students, the back panel and sub-VIs are all still available, and we see students use the VIs as a basis for capstone design projects and hobby work in our campus makerspace.